There's two sides to data structures, and we're going to eventually explore how they work, but the other side is how they're used, how they are available in a lot of languages as common tools that you can just utilize out of the box. So one of the ways that they're sometimes called, and I'm going to use a lot of Java terminology here because that's kind of what is I'm most familiar with, but they're sometimes called collections, where they're just there for grouping a whole bunch of different objects together. And so, really, most of coding is about storing individual values within a variable. But when I want to store a bunch of the same thing, like our picture of eggs here, I want a dozen eggs, I want 18 eggs, however many eggs you're going to go buy. You have some structure, like the egg carton, that helps you hold them all together. An array is the most basic of those structures because they can all just be set next to each other, and that's kind of what the eggs look like here, a multi-dimensional array of eggs, if you will. But there are other strategies for creating these. But at the high level, the notion of a collection is a self-managed storage system. So an array has a fixed size, and you put things into the array, but we typically don't make those bigger, or if you do, you have to copy everything over again. There's a lot of extra work around there. By putting this idea of a collection, encapsulating the actual storage mechanism around it, you can use an array, and there's are many data structures that do, but then it'll automatically get bigger if you fit the size of the array. So like our little seating here, if we fill up everybody in the room, then we have overflow sitting in the next room, and the speaker doesn't need to think about it. They just keep talking. Um, so collections have some basic functionality like inserting, deleting items, and adding and removing whole groups of items at once. Here, add these 10 items in, or delete everything that from the collection that matches this criteria. But the whole point of this is, as it says, the encapsulation of a bunch of behavior that you would have to write yourself if you were dealing with just a basic array. So there's a hierarchy of collections, and I'm going to again use the Java terminology here. So in the Java world, you have a collection interface and you have sets and lists, and the same conceptual breakdown works well across most languages. So a set is a specific type of a collection that only keeps one of an item, and we're going to see more of that as we go into here. And then a list keeps a whole order to the items in various different ways. And as you can see underneath that, there's many different types of these. Mostly the change between these is how data is stored. And that's what you'll learn more about as we go further into data structures, is the different ways we can create these data structures and the advantages and disadvantages of each. In some cases, they also add additional functionality, like when we talk about stacks. And so we'll talk about each of these in turn, but know that they're all kind of related to each other. They all start with this idea of a basic collection. So the basic collection sometimes is called a bag because when you have a bag, like if you're playing Scrabble, that's where my inspiration for this picture came from. You can reach in and pull a tile out and you get a letter, but you have no idea what letter it's going to be. You just are getting something out. They don't come out in any order. There's multiples of some letters and singles of others, and there's a whole lot of a few. But I can add and remove things to a bag just kind of haphazardly. The most important thing, though, is I just do not know what's stored inside of a collection. So in reality, there is no such thing as a collection as far as an algorithm goes, as far as actual data structure goes. It's always going to be a list or a set or some other structure. So when I deal with a collection in a language like a Java or other languages that include that notion, it's just saying I have a group of data and I can work with that group of data as a user, and I don't care how it's stored. Somebody else figured that out. Think of it this way. You take your recycles. In some places, you separate glass and plastic and all different, each individual one, where in other places you just put it all in one and you dump it in a container, and somebody else sorts out the glass from the plastic from the metals later on. Um, so the bag is kind of like that second paradigm where I don't put any structure to my recyclables, they just kind of go get tossed in. So coming back to this idea of a set, the set generally also acts kind of like that bag. The biggest difference between a set and all other types of data structures is there's a rule that says I have one and only one of a thing by whatever the identity rules for that thing is. So in Scrabble tiles, the bag would at most hold 26 tiles, A through Z. It wouldn't have copies. There wouldn't be second tiles. So if I added in these three items, A, X, and Q, the A would not get added into the final set. The set right now is 3 items in it. I add 3 more. It would only have 5 items in it. It doesn't allow duplicates. Now, behind the scenes, there might be some ordering internally to this set. I don't know. I have no way of knowing when I deal with a set unless I know what type of set it is. So just remember, there's 2 levels of abstractions that I want to be aware of. Is one's the behavior. Do I have just a general bag, or do I have a set that's going to be a little different functionality, or a list, or some of the other ones we'll see later on? And then the next level of abstraction is, what are the rules behind that? So some structures, like a tree, will automatically order the items in your set, where other, like the hash set, will not. And there's still other options inside of there as well, as far as algorithms go. So the idea of a list is exactly the opposite, where a list, like our little train analogy picture here, is things go onto the list in a specific order. And typically if you call the basic remove function, they come back out in that order. So it's what's often called a first in, first out when you're dealing with the basic list. So the Q was the first one added, A came after, J comes after that, Z comes after that, A comes after that. Notice second A. These all come in order of which they're coming in. So basic list is just like this. It's your grocery list. It's your your class roster. It's your to-do list. They're just stuff that just happens to be down in the order in which they're written. The cool thing about lists is I can modify it. I don't have to do my to-do list in order. I can jump to the 4th item on the list if that is the most important, or the easiest, or the most desirable at the moment. You can do that same sort of thing within dealing with a list. So they're very flexible, and probably the most common data structure used in code. Later on, we'll talk about this idea of a map, which is sometimes also called the dictionary. And the idea of a map is there's some sort of relationship between a key and a value. The best analogy I can tell you is a library. So if you want to go find a book in a library, you don't go typically alphabetically through the title. Some will put them alphabetically by author, but often there's a much easier way, which is like the Dewey Decimal System, or the other different reference systems for libraries, where I can look it up by topic, I can look it by subject. I have some sort of other way I look up some number, and then I go find it on the shelf at that location with that number. That's, and again, analogy, don't take it super literally. But the idea is still there, and the idea is still valid, where a map allows me to store a value using some different key inside of it. And we'll see in a video exactly how powerful and useful this is as far as coding goes, when I want to especially cross-reference and look up data in a variety of interesting ways. So this is just a quick overview of the types of data structures we'll talk about and how they're used. By becoming really familiar in their use, which is what we're going to do this week, I think it'll be easier to understand their implementation and the trade-offs later on. And so that's what we're going to focus off to get started, is get you really, basically knee-deep in using these things, not any deeper than that. And then we'll really start to look at their construction and how their logic works internally later on.